විතරක්
Yes.
මේ අක්කේ මේ මොකද මේ පොඩ්ඩක් මම මේක ෂෙයා කරලා බලන්නද YouTube එකට? දැන්
ආ
අපේ
එල කේස් කේස්.
පොඩක් චෙක් කරලා බලන්න වගේ.
හරි.
පොඩ්ඩක් කට්ටිය කතා කරන්න එපා.
මියුට් කරගන්න ඉන්න.
kindly stay with us for a few minutes as we wait for the rest of the participants to join. We'll be starting the session shortly. Thank you for your patience. Good evening, everyone. A heartfelt welcome to Towards Autonomous AI Systems, the Session 1 of HackElite 2.0, organized by the IEEE WIE Student Branch Affinity Group of University of Muratoa. We're truly delighted to have each and every one of you with us today for what promises to be an intellectually enriching session. Before we dive in, feel free to use the official virtual background. It's already shared in the chat, so you can grab it anytime. I'm Janati Kodikara, and I'm honored to be your host this evening. HackElite is the flagship competitive innovation challenge organized by the IEEE WIE Student Branch Affinity Group of University of Muratoa. It's a platform for creativity, teamwork, and impact from ideas to prototypes. And today marks the first session of this exciting journey. Let's take a moment to recap HackElite 1.0 through some snapshots. From brainstorming ideas to moments of creativity and teamwork, these highlights capture the energy, collaboration, and spirit that made the event so special. And now, with HackElite 2.0 just around the corner, we're looking forward to an experience that's even more exciting, more inspiring, and even more memorable. Today, we delve into a fascinating and cutting-edge topic, towards autonomous AI systems, where we dive into the future of intelligent machines and their real-world potential. If you have any questions or thoughts during the session, feel free to join the conversation. Just scan the QR code on the screen or go to slido.com and enter the event code to drop your questions. Let's make this an interactive and thought-provoking discussion. And now it's time to welcome our distinguished guest speaker, Ms. Prashani Jayasinghe, a doctoral researcher at the Faculty of Science and Engineering, Abo Academy University, Turku, Finland. She holds a MSc in IT from Abo Academy University, Finland, and an MSc in Engineering from Esteghlise, France. Let's warmly welcome Ms. Prashani Jayasinghe to take over the session. Over to you, Ms. Prashani.
Hi, thank you so much, Jinati. Okay, so hi everyone, I am Prashani. I don't think I need any more introductions because Jinati already did it. I will dive into the presentation. Let me quickly share the screen. Okay. Okay, can you, I hope everyone can see the screen. Okay, so hi everyone. Like I said, I'm Prashani. Let's talk today about autonomous AI systems, or going towards autonomous AI systems. During this session, as Jinati said, I would like a very interactive session, so please feel free to ask me any questions. You can interrupt me anytime. And I will also kind of ask you questions and try to engage with you so that this conversation is not monotonous. And I hope you guys will turn on the audio and actually answer my questions. But don't worry, there are no wrong answers. So let's dive in. Today we are going to talk about really a short introduction of AI and a very brief introduction of the history as well. And then as we know about large language models and what exactly are AI agents and agentic AI and how we can compare these, and then about RAG-based systems. Oh, no. Okay, so before I actually go to the next slide, I want to ask a question from all of you. Feel free to write it in the chat or just open your mic and you can answer me. It's a very simple question because we are going to talk about artificial intelligence. Can someone tell me what exactly you think is the definition of artificial intelligence? I'll give you a few seconds, maybe 30 seconds. You can also raise your hand. what you think is the definition of artificial intelligence, or what is really artificial intelligence. I hope you did not see my next slide. No one? Someone?
It's the creation that like humans.
I couldn't hear you. It's the creation of human. It's almost a good answer.
It's like human intelligence, which make computer.
Okay, yeah. So I also got another answer from here. AI is the development of computer systems that can perform tasks requiring human intelligence. So a very famous quote is like artificial intelligence means mimicking human intelligence, basically. However, in reality, there is no one true definition of artificial intelligence, because over the years it has combined so many different technologies and methodologies, so you cannot equate it to just one single sentence. So according to the famous words by GPT-4 itself, there isn't one single true definition of artificial intelligence, but there are several widely accepted definitions. So yeah, on the right side, I just put a small picture just to show you the depth of AI actually. If you know the depth of the ocean, you will understand this. But yeah, so there are a few definitions that I can actually say. These were given by very famous mathematicians and scientists who were very prominently engaging in the field of artificial intelligence since the 1960s. So AI, for instance, McCarthy, who coined the field of artificial intelligence, or who coined the name artificial intelligence, actually said that AI is concerned with methods of achieving goals in situations in which the information available has a certain complex character. These methods that have to be used are related to the problem presented by the situation and are similar whether the problem solver is human, a Martian, or a computer program. And then Niels J. Nielsen and Jan LeCun said something quite similar, but you can see that because they are mathematicians and different scientists and they work on different systems, their definitions are different. So when it comes to artificial intelligence, there is no true definition. There are widely accepted different definitions. Okay, so a very small history about AI. AI really started in the 1940s, if you were not aware of that. So it started a really long time ago with something called symbolic systems. So symbolic systems is basically a rule-based system where you basically describe how the world is perceived and give a set of rules. And based on these rules and based on the observations in this perceived world, it can make some conclusions. So it was highly driven with rules and regulations. And then in the 1960s, the boom of machine learning came to be, where we now also see the usage of data. So vast amounts of data is used to learn about certain features in different contexts. If you want your AI program to identify a cat, you can put millions of cat images, and then it's going to be able to identify certain features of the cat. So it can then say this is a cat instead of a dog. So that came in the 60s, and then now, of course, I don't have to, I think, say anything about LLMs. I'm pretty sure all of you have used large language models, at least Copilot or GPT-4 or whatever, hopefully in a good way. But yeah, so now in the 2020s, you can see the boom of large language models. So one thing you need to keep in mind is, even though you feel like LLMs are kind of, we are at the brink of AI because it's so powerful, they can reason and give you certain explanations, but they cannot perform actions. So they are basically tools, and you cannot call them agents. And I will dive deep into what agents are basically. But LLMs are really powerful computers with natural language processing, to kind of give you a very basic definition. Feel free to ask me any questions in the middle. You can also put it in the chat as well. Okay, so one example of symbolic AI in the early 1940s would be ELIZA, if you have ever heard of it. Actually, it was the 1960s. So this is a very simple chatbot which was rule based. So it cannot actually go beyond the rules that have been established within the system. So you can see how very generic or very shallow this conversation is. And then on the right side, you have object detection that came to be because of machine learning, because of all the object recognition, and also because of vast amounts of data. So there is a reason why there isn't necessarily a big giant definition for AI, because it's such a big impactful set of technologies and methodologies that still keep expanding. So over the years, definitions can change, and you can add more concepts. So if you can see, the image here is basically a giant universe of what artificial intelligence looks like. So you have AI as a whole, and then you have machine learning, and a subset of machine learning is neural networks, and a subset of neural networks is known as deep learning. Okay, since we are using large language models, I also wanted to give you a small understanding on how it actually works. I hope you know it, but I will still give you some key information. So I don't know if you have tried GPT-1, which was created, I think, maybe 5 years ago or 4 years ago. I have tried it. It was very, very simple and monotonous, just like Elisa. It was not able to answer correct questions, or it, like, at some point it is really inaccurate. And thanks to what we call this transformer architecture. So this was a neural network architecture that came to be. You can research on it because it was actually a big thing that revolutionized large language models. So the transformer architecture was one of the most base things that was really necessary. And then you have something called BERT. BERT is bidirectional encoder representation of transformers. So what this means is BERT is a method of moving information in two directions instead of one. So you can actually move information from one place to the other, rather than it just going in one direction. And that also made a huge impact in large language models. And then the parameters, which is highly spoken of. If you check from GPT-1 to 2, 3, 4, you can see how many parameters increase. And that's actually one of the reasons that large language models like GPT-4 works much better than GPT-2, for instance. So I'm taking GPT as an example, but that's not the only LLM, by the way. But the parameters, of course, is a really big thing that really help with tokenizations. And then you have multimodal systems. So multimodal system means the input and the output can be of multiple types, which means it can be of text, it can be of images, it can be of speech. So for instance, if you ask the LLM about something that the LLM is going to read from Wikipedia, instead of it reading just the text, it can also recognize the image. And if there is some kind of speech recognition module in the Wikipedia, it can also read from that. So the information is much more accurate as opposed to you just getting the text. So this multimodality was also important. And now you can, of course, see in many LLMs, or even in OpenAI, that you can type something and it's going to output like a slide or presentation or some kind of graphic that you can use. So LLMs are deep learning modules, and they are transform architectures with billions of parameters, and it's mainly with natural language processing that is used for text generation, summarizations, and translation, question answering. I mean, you probably use it every day at this point, so I don't think I have to say anything about it. But yeah, this is kind of the background of large language models. And according to the Financial Times in UK, there the history basically, large language models is not separated as something really like a core information or core structure for artificial intelligence. In reality, there are three waves of AI. We call it three waves of AI. So one was the symbolic systems, the second was the machine learning, which was expert systems, and the third was neurosymbolic systems. But according to the Financial Times, LLM has also brought in a big revolution, and they expect in another 3 years, for instance, that 70% of customer interactions in the industry around the world will be done by AI bots, and 80% of businesses basically will start using chatbots by 2025, which will, I mean, they are already using it anyways, but they will integrate these open AI systems. And of course, there are restrictions when it comes to LLMs, and they did a small survey to figure out like why they think the employees are using these generative AI tools even if they are not approved. And most of them have different kind of answers. So it helps with their jobs. They don't see any risks. Employees cannot check, explore new tools, lack of clarity, and so on. So there are different reasons why you would use large language models, even if you are asked not to. But let me check the next slide actually. Yeah. So there are multiple reasons you would or employees would use LLMs, but it's a very interesting fact that I just wanted to put here. And my message was basically, is LLMs good or bad? Any hands who says using LLMs is bad? Is there anyone who has never used GPT or any kind of large language model? Copilot, DeepMind? No? Okay, good. So lots of researchers in education, especially, because I think that's where one big problem lies, because we as PhD researchers or whoever marks your coursework cannot really, now you can identify if it was GPT, but you still, there are ways you can, change those things. And they are also afraid of you losing your creativity or your innovative, ideas that come into your mind because of GPT. But it's important to remember that, uh, yeah, it's important to remember that, LLM is such a big tool that you can actually leverage, because it is going to give you really good answers. Even it might not be accurate, but it's going to give you really good information as well. So don't make it think for you, but of course you should use it in the correct way. If you want to fact check, if you want to say, yeah, I have this idea, what do you think? Are there people who have done it before? Do you want to check if this is a feasible idea? If you want to see, you want to do a different kind of innovation, what is kind of a project plan that you can have? So you can actually do lots of things with LLMs, but don't make it do all your work. So have your creativity, have your innovative ideas, but of course LLMs is going to be kind of used in everyday life. I think at this point in maybe the next few years, everyone is going to use it, and we really need to adapt in the correct way of using LLMs. So remember to use LLMs in a effective way instead of, making it complete your assignments if that's what you're doing. Okay. So before I move on to explaining to you about AI agents and agentic AI, let's take an example that we can actually ask ourselves and also ask GPT, just to see what information it's going to give out around this question. I want to plan my vacation to Japan in September. So let's say I want to plan my vacation, and everyone, all of you want to plan your vacation. So if you don't imagine, there is no GPT, you have your phone, you have internet, you have all the stuff that you need in your hand. What are the things that you will actually do when you're planning a trip? You want to go to Japan from Sri Lanka. So I will write one so you can actually understand what I'm saying. For instance, I need to find accommodation. What else do I have to do? Dates. Yes. So dates in September. Good. So when you are available for vacation. What else? Language. Good idea. What language they're speaking? Is it English? Can I survive with English? What else? Dates, flights, budget. Very good idea. Of course, you need to check your budget. You need to find the available flights. What else? Places to visit, transportation. Good. Places to visit, transportation. Oops, where did I write it? Transportation. And I'll just write here maybe visa application. So yeah, you have a bunch of steps you have to do when you want to plan your vacation to Japan in whatever date. So I have written September. Good that you guys did a good job here. So yeah, so your goal is to have a vacation to Japan, and if you are going, you have to follow these steps. So if I ask this from GPT, so I said plan my vacation to Japan in September. So it's going to give you some small idea on it, and then what to expect, and it's going to give you an itinerary, then some planning tips, and then just what to eat, what to pack, and a summary. So some of the things that we actually wrote down, it does for us. It doesn't do, it just says those things, so gives you the information correctly. Okay, so you saw how GPT works. It basically gives you certain amount of information through certain amount of reasoning. So it reasons with all the information that's there in the internet, and then it does some kind of processes, and then it kind of gives you the information. So one thing that we need to keep in mind is that LLMs will help you think and plan, but it will not act, reflect, and perform autonomous tasks. So what it means is that when you write, plan a vacation, it's not going to act on the information that you have given. It's just going to help you think and kind of do some processing and then just give you some information. So it's not going to act or reflect or do any kind of autonomous task. So again, if I take this, plan my vacation to Japan in September, I've written something quite similar to what we were talking about. So budget, accommodation, food, application, transport, and so on. So even when we are doing these kind of things, we do it like step by step, or we do it in like blocks. So we think about the budget separately, we think about accommodation separately. So we can call these different kind of building blocks to get to our goal to go to Japan. So you can actually break these down into different kind of building blocks. And if you are going to really code this, like forget about like large language models, forget about like AI, for instance, and just think about you want to code like separate blocks for these. So you want to build a trip itinerary. So you call an API from the internet and you build something. If you want to check the weather for the certain dates, then you can do the same. You can call the API with the API and check those. So you can code these, for instance, separately, like block by block. And these separated tasks are actually called agents. So in artificial intelligence, an AI agent is a system that autonomously performs tasks by designing workflows with available tools. So the example that I showed you now is a multi-agent system. So you give a goal saying, I want to plan a vacation to Japan in September. So these agents, or we actually code these agents. So you can have a trip agent, a weather agent, a visa agent, a flight booking agent, and each of these building blocks is going to do a certain task independently from another agent. So these small building blocks are actually called AI agents. Uh, so you can actually build these AI agents using code, using AI, using whatever. And you can also give a goal to these agents. So for instance, if your trip architect agent is just to plan an itinerary to Japan, then your whole model is only going to be giving you vacations uh, plausible to Japan. But if you have, for instance, a trip architect agent with lot like PDFs of information saying this is how Japan is, this is how UK is, this is how Canada is, then you have to go find that information. So this is an agent where you are going to do a certain task according to the goal that is given to you. If you didn't understand, just tell me, okay? All right. So there are different techniques of these AI agents. So the first one is react. So that is reasoning and acting. So it combines reasoning of through large language models, and then it uses a certain tool or any kind of tool. So let's say you want to find out uh, a medicine or how much dosage of Panadol you should take as a 30-year-old. So you type it, actually GPT now has agents. So if you type it actually in GPT, for instance, what it's going to do is it's going to call an agent which is very specific to medicine as opposed to it just generically finding information. So this way information is really specific. So it's going to call this medicine agent and say, okay, I need to find this information, and this medicine agent will only go to internet or wherever and find medicine related information. So that is an agent. So it's, you can have an agent for finding images of cats, you can have an agent for finding information about the universe, and so on.
Excuse me, ma'am.
Yeah.
So, ma'am, if you take a model that contains several agents, is it a, is it also an agent of like a collection of agents?
Can you repeat the question? If you take?
If we take a collection of agents that
Mm-hmm.
can perform various actions and things, so
Mm-hmm.
is that the collection is that model that has a collection of agents is also an agent because it can perform tasks
So
separately?
yeah, I'm going to go into what is agentic AI, but I see
Yeah,
what you mean. What this does is basically you are the one, because this needs human supervision. So if I say plan my vacation to Japan, I need I'm going to ask the LLM, okay, break this sentence down to smaller steps. So let's say Japan and vacation and September. And
yeah.
then using those three things, then those three goals will find these agents. And these agents are already established. So you have already programmed this agent somewhere in the back. So the whole framework is like human supervised to a certain extent. But it can do one step more than what you would find, let's say, in just natural language processing. Did
All
you
right,
get
ma'am.
it?
Thank you so much. Yes,
Yeah.
thank you, ma'am.
So then you have chain of thought, which is basically encouraging the LLM to break down complex tasks step by step, as I just said. And then you have tools used with LLM, so integrating APIs like the weather API and whatever. And then you have finite state machines, which means it's going to define states and transitions for handling these tasks in a structured way. So for instance, I can also tell you that these agents can work parallelly because they're independent from one another. And then you have multi-agent collaboration, which means then it works like together to a certain extent. Yes. So now we came from a natural language processing where you have giant amount of information to AI agents where this information is broken down into building blocks, and these building blocks have smaller tasks, and those tasks can be performed like simultaneously or independently, but those tasks are quite defined and they react based on the reasoning or the steps that has been given on the top. But what would AI look like if it can plan, reason, and act on its own? So, for instance, what I'm going to say is, what if I can say, okay, can you book me a flight? Just that to Japan. What it maybe this autonomous AI system can go to your calendar, check the free dates, go to the Google flights, then check for available flights, check your budget, and just say, okay, you have 300 euros and also book the flight. So it is going to do all of these and you don't have to do anything. For instance, that's what autonomous means. Or if you want to book a hotel, same procedure. So what would that look like? So that is called agentic AI. Agentic AI refers to a system with agency, the ability to autonomously research, plan, and act on open-ended environments. So you don't have to specifically mention, go here, book the flights, take the money, book, like go to this website and book it. But it's going to have an open-ended understanding, and of course it's going to learn by itself, but it is able to achieve goals based on just one simple step that you have given. So unlike basic agents, these systems demonstrate initiative, adapt to unexpected situations, and can persist across tasks without human input. So this is a higher level concept, which also kind of encompasses AI agents. Okay, I hope you understood the difference between AI agents and agentic AI. Agentic AI is like the whole framework with really minimum supervision, and AI agents is basically supervised because you are going to define the tasks and also define the breakdowns. But these breakdowns, if they're autonomous, then that is kind of like agentic AI. So they also have different kinds of methods. So deliberative planning and reasoning, which is kind of, it's going to plan multiple steps ahead. So if you say book a flight, it's going to do it on its own. You don't have to write that you have to go here and check the flights here and then you have to book. It's going to figure that out on its own. Then you have self-reflective loops. Think, act, observe, replan. So you think, you act on it, you observe if it is a good thing or a bad thing, and then based on that you can replan. Then you have hierarchical agent architectures, which are like high-level agents that delegate the subtask to specialized worker agents. So big agent giving tasks to smaller agents. And then you also have integration with retrieval augmented generation, which we will talk about soon as well. So if I were to compare AI agents and agentic AI, so AI agents are what we call reactive, which means it's going to reason and then act on it. So reasoning part, and then we have given like, if this is the case, then these are the things that needs to be done, and then they go to these agents. But agentic AI is proactive, so I don't have to tell them do this, or find these agents. It's going to take those agents and do things on its own. Then you have different methods, as we said. In environment, or as a, if you have a framework, of course AI agents are quite constrained because you have defined the tasks, so it's only going to do what you have said. In the sense, if I'm saying plan my vacation to Japan in September, and when you give this, you're going to break it down like plan your vacation, let's say just Japan vacation and September, and then you're going to give it tasks. then it's going to only be able to do that, as opposed to agentic AI, which will have reflective or open-ended kind of environment. I think somebody has a question.
Excuse me, ma'am. So, ma'am, if we take AI agents and agentic AI, so like, what's the most effective if we take? Because like we can see like AI agents like need some more inputs than agentic AI, right? So I think, hello.
Yes, sorry. Just give me a moment. Something happened to the
All right, ma'am. Sure.
Yes. So you ask what is more effective. I
Yes,
would
ma'am.
say,
Because
yeah.
yeah, ma'am. Yeah, go ahead.
Uh, I would say that it depends on your the tasks that you want to do, and also kind of, if we look at like product based solutions, in reality, of course, money matters. It matters like what are your requirements when you're building these kind of
Yeah.
systems. So if you're building in large language models, of course I would say agentic AI. But if you're building something smaller, I would go with AI agents, specifically because let's say you want to build something in the medical industry and you are coming from a pharmaceutical company and you just want to know information about your medicine, your pharmaceuticals. You have different kind of, let's say, documents and guidelines and whatever. So this is limited or finite set of things that you have. So in that sense, if you, because it's medicine and it's really important to get those things correct, I would opt for AI agents, because you need a certain amount of human supervision, because you have to give really accurate information, as opposed to you want to do something like innovative or proactive, that like planning a trip. You can actually let the agentic AI learn by itself and have like, you just don't, not even Japan, you want to plan a conference to like UK. So now the goal is a little bit different, but it's almost the same. So now it can
So
kind of learn from what it has done before. But it really depends. You can also use agentic AI to that pharmaceuticals, but you also have to understand that when it's open ended and when it's a dynamic environment, then there's uh, there, I wouldn't say there is room for error, but you might not know what is going to happen. So that's a little bit of a risk. Did you have
all right,
another
thank you, ma'am.
question? Okay.
No, that's all.
So
Thank you.
as the example even says, I would opt for agentic AI for self-driving cars, because it has to be dependent on certain systems, as opposed to LangChain or AutoGPT, which is kind of not, it's not necessarily finite, but it can have like very structured information or structured set of kind of rules or things to do, as opposed to self-driving cars. You can like, you cannot 100% say what's going to happen in the road. There can be a million different scenarios, there can be different systems integrated to different systems, and how everything is going to react. So it's going to be different. So, for example, agentic AI is used in self-driving cars, and AI agents are used in like LangChain. Okay, so quick comparison. Uh, AI agents, which are reactive. So what happens is you say find flights from London to Paris, then the agent searches the flights. Then you have to ask a hotel, like find the hotel, and then it has to search for a hotel, and then you can ask for a 2-day itinerary, and then it suggests an itinerary. So it's like 3 different agents that will work on this. But if you take agentic AI and say plan a weekend trip to Paris, it's going to break these down, and you don't necessarily have to ask step by step. It will say, okay, if you want to go to Paris for a weekend, you need flights, you need hotel, you need itinerary. It will come up with its own set of things like we did when we were going to plan the trip. So then it will execute those steps using the AI agents again. So just before we move on, I just want to make sure you understood the difference between AI agents and agentic AI. In agentic AI, of course, you can have AI agents inside. So this kind of actually performing this task without human supervision is kind of agentic AI, if you like, if I really think about it. Okay, no confusion, hopefully. Okay. Okay, before we go to RAG, just give me 1 minute. I just want to, yeah, give me 1 minute. Okay, so I think I went a bit quicker, but if you have questions or if you didn't understand anything, please let me know, okay? I will try my best to answer as much as possible so you understand autonomous AI systems basically. So has anyone worked with RAG before or heard what RAG is, for instance? Okay, I'm thinking it's a no. Okay, so RAG is a kind of methodology which is in long form, it's called retrieval augmented generation. And this has been a really powerful method or technique that is used in LLMs or in basically chatbots or anything related to getting information. So as the name says, it's retrieving information, retrieval augmented generation. So generating information based on retrieval. Okay. So retrieval augmented generation is an AI application that connects Gen AI models with external knowledge bases. The data in the knowledge base augments user queries with more context so the LLM can generate more accurate responses. So I can, for example, take the same medical database or medicine information that you want to ask a large language model. I would be more uh, happier or more, I would trust, let's say, I would trust more an AI that can actually, when you ask for, let's say, you want to ask what is the dosage of Panadol you can take as a 30-year-old. I would trust more if this information can actually be reasoned and searched specifically only in medicinal, like accurate medicinal databases, as opposed to using generic information, because in the internet there is so much information and one can contradict another. So having this knowledge base and attaching this knowledge base to a large language model make sure that your information is contextually accurate. So if you look at the, let's say, the pipeline of how this works is basically you have a query or a question, and based on this query or question, you're going to ask, you're not going to ask anything actually. You're just going to ask the question, and then based on this question, information is going to be retrieved. And then you have a prompt that's going to generate the answer based on the retrieved document. So let's say you asked about, like I said, you want to know what is the dosage of Panadol you want to take, and then the retriever goes and finds in the medical database or drugs.com or somewhere where you have Panadol specifically with specific information, and then it searches the dosage and then it gets back, and then the prompt is going to create a user interactive answer. Instead of it just shooting out dosage amount is this, it's going to say for a 30-year-old the dosage amount is going to be like this, instead of just saying dosage amount equals this. So that's why you have the prompt and the LLM here, and then you get the answer. So why RAG or why it's such a powerful tool is because of many reasons, and I think now it's going to be, I mean, it's already really popular. So what it does, it adds external knowledge to large language models. So if you want domain specific knowledge, like I said, I go to medicine because medicine, for example, is really important, where you should not change the information, or information needs to be really, really accurate. So domain specific knowledge as opposed to generic knowledge in medicine databases or medicine is really important. So that's one thing. And then you have reduces hallucinations. Do you know what hallucinations are in large language models? So yeah, so you know, that's good. So hallucinations are basically when there's so many information contradicting, or you have too much information on one thing, it's going to like put some, we call it garbage in garbage out system, where you're not going to get anything correct. Yes, it's like guessing. Then it also can handle large amounts of data efficiently, because it's going to do something called a vector search. We can see it soon. And then it can cite sources for transparency. It's quite lightweight because you're not attaching all the like information in the knowledge base. You are asking to retrieve something from somewhere, as opposed to attaching the 100,000 information in the LLM. It has persistent memory simulation, which means that you can store, because now you're going to store this vector information. So it has a memory. And then it keeps AI responses up to date with the latest information. So you, instead of you having a specific document or downloading something from the internet, you can also attach the URLs, for instance, and that can go and search like the website. So if the website is updated, then you can retrieve information like in real time, as opposed to you updating your PDF all the time, for instance. So these are some reasons why RAG has become quite impressive and important. So if I zoom in more regarding how this pipeline, or how this pipeline as a whole would look like, you already saw like a generic design of how it looks. So this is like a smaller understanding. So if I zoom in more, this is how kind of a very generic RAG based architecture would look like. So on your left hand on the top here, you have all the documents. I can take like medicine documents. You're from a pharmaceutical company, you have 100,000 documents. And what happens is all these documents are then broken down into smaller documents, or smaller subsets of information. And these subsets of information is then stored in a way that the LLM or the computer can understand, or actually stored in a way that the information is much more rich in like features. I can explain more later, but this is called vector embedding. And these chunks are then stored in a vector database. So when you ask a question here on your left bottom, your question is also embedded as a vector, because the way the retriever works is, if you have, for instance, I can tell you in coding, if you have a string and if you have an integer, and you ask to add the string and integer, it's not going to be able to add it, because there are two different data types. So it's quite similar thing, where you need to embed your question in a way that the retriever can understand and actually take from the vector store. So both your question or the query that you're asking, and also the information you get from the PDFs, are both going to be vectorized. And then it goes through a retriever based on whatever you ask. Is going to take the information from the vector store, and then it's going to pass to the LLM, and the LLM is going to use that information to give you a very whatever answer that the LLM has based on your RAG. So first, if you want to build this is quite easy to kind of build, and this is very, I would say, important if you are working with like really specific. If you want to, like, for instance, in websites, create chatbots just about your company, I think this would be one of the best things, because you can integrate LLM with all the documents in your company, for instance. So first thing when you're building RAG is you need to build the vector store. So all this here, all the chains or all the movements here is to kind of build something for the vector store. So first, you have to create your own information or your own database or use existing ones. So if you're creating your own database, you need to have a storage system. And usually when you're creating your own database, we have something called ChromaDB. But if you're using existing ones, you also can search in the web Pinecone and Viviate. So these two are already existing vector stores with some information that you can actually use. So you can collect like necessary documents, you can collect like necessary URLs, which is like websites, and or gather PDFs to like one folder. You can directly call the website through a web-based loader or use the Playwright library, or you can use this platform called Firewall. So you have to first take the information. It's basically like opening, I will show you the code soon. It's just you take all the PDFs to one folder and like read them into your code. Or if you want to use URLs, which is like directly access websites, then you need a web-based loader. So Playwright library or Firecrawl. Then you need to take that information in your PDF or website and divide it into different chunks of information. So when you're dividing, we call this actually splitting. There are different ways you can split the information. So you have character splitting, which means it's going to read the million characters and you're going to say split them to 20 characters, and every 20 characters it's going to form a chunk. Or you can say sentence splitting. And this is something used quite often, because when it comes to sentences or paragraphs, for instance, like if you take a paragraph, usually a paragraph ends when like the semantic context ends. So when you're beginning another paragraph, usually it's something a bit newer than your previous paragraph. So having that whole paragraph in one chunk is better than you breaking that information into two. So sentence splitting is also good because you can split from the full stop instead of midway. So you can say every 5 sentences or every 2 paragraphs or whatever. Then you have token-based splitters, because tokens is what is used in LLMs. Then you have recursive character-based splitting, so splits in natural boundaries, or you can do custom splitting. So you split like you can customize. You can split any way you want because it's a document or a URL. It's just having lots of information and you just split it however you like. But my opinion is you should do this sentence based splitting or paragraph basically. Once this information is split, then you need to embed this information. So this information can be embedded very easily already, because now OpenAI has embedding modules, and then you have something called Hugging Face transformers. So they are kind of good for like if you want like many tasks to be done. But if you want a general purpose one, I would say OpenAI embeddings. So I will tell you also how this embedding works in a moment. I couldn't add it in the slide. So once this, now actually you have built the vector store. So you created the documents, then you broke it into chunks, then you embedded the information, and then you store it in ChromaDB, or you can use also existing vector data stores. So then you're going to retrieve that information. So that's where you have a retrieval. And there are different retrieval methods. So you have similarity search. What similarity search does is it's going to find vector similarities. So for instance, let's say you want to, you have the word cat, let's say, in your PDF. The cat is blue or the cat is white, and what happens is when you're storing the word cat in the vector database, it's going to give some numbers. So let's say the cat is identified as 2, 6, and 5. And in your question query, also you have the word cat. And it also has 2, 6, and 5, or some similarity between those two words. And since you have both of them in vectors, now it's quite similar. So you can do something called similarity search. So similarity search is basically you find similar kind of uh, features in the vector. So this is based on what we call cosine similarities. You do cosine function. And then you have something called max marginal reference. So it balances between relevant documents and diverse information attached to the relevant documents. So if you're asking information about the cat who is Garfield, if you want to know more information, if you're asking who is the author of the Garfield film, for instance, the retriever can just give you the author's name. But if you're using max marginal search, it can also give you an extra kind of step saying this is the author from Garfield and he has also done these movies, for instance. So instead of it stopping in one place, it can give you some more diverse information. And then you have something called similarity score threshold, where they create the similarity score for all the vectors and then similarity score for your queries and see how the query and the question are similar or how certain vectors are similar. I hope you understood all three of them. No questions? All good. Okay. So that is basically RAG. If I just want to go back to show you here. So you take the information, break it down, embed it, and store it. And then you ask the question. This question is then vectorized, and the retriever does some search understandings of it and then gives you information. And the LLM makes it like human readable, basically. Okay. So now you just understood if I'm asking one question, but you can have a full blown conversation with this. So not just like one time asking the dosage of Panadol. Maybe you want to also ask, is it like what kind of drug is it? Or you can also ask about some anti-inflammatory drug. So you want to ask multiple things and you want to keep the question going. So here we use something called prompt engineering. So prompt engineering is the art and science of creating effective instructions for AI modules to give better results. So what you are doing is, if you're asking questions just about medicine, you're going to say, for instance, you have a question based on your previous questions in this interaction, based on the knowledge base that you have, formulate an answer that is going to be asked now. So prompt engineering is really powerful as well. Even I think you have already heard about prompt engineering because uh, you in GPT specifically, if you want to know something, they say the better the question, the way you have formulated the question makes your answer much better. So it's kind of similar to this. And then you have RAG, and then your OpenAI can answer for you. So if you want to build RAG, because it's quite easy, you can also go to this OpenAI LangChain module in the internet. It already has like a guide to how you can create these prompts, and it also have examples of these prompts. So you can actually use those. Or you can use your own and see how you can twerk on the way it understands the prompts and actually get the task done. Okay. Before I go to hands-on practice, do you have any questions? Did everyone understand everything? I'm going to ask a quiz now. I'm kidding, but I hope you understood how RAG works. Do you have any questions so far? Okay. Feel free to ask or type questions as well. Okay. Yeah, need to research and learn. Yeah. Yeah, I gave you kind of the very basics of all of these AI agents, agentic AI, and RAG. But these are all powerful. For instance, RAG can be an agent because it's retrieving information. So you have an agent that retrieves information. That can also be like one AI agent. Yes, I can give you the slides set. Okay, let me share the code. How do I? Okay, I hope you can see the code. I did this quite a while ago, but okay. This was just a testing. Okay. Yeah. So if you look at my code, the first code is just me taking information and splitting it and asking it a question, or actually just storing it in the vector store. What you just need to know is first you define the directory containing the text file. So if you have a code or if you want to use Visual Studio or whatever, you give the path of where all your information is. So let's say you have 100 documents in some folder 1, so you give that. And then you write the, if you want specific documents from that folder. I mean, this is basically, this is not even AI, this is just coding. Is there anybody who has not coded in Python before? I'm sorry, I couldn't even ask that. I hope you can see my screen, hopefully. Yeah. Okay. Yeah, so you define the path to your documents, and then you have to check if your Chroma store already exists. This means that if you have already built a vector embedding for one PDF document, you don't have to build it again because you're storing it. So without wasting storage space, of course, you have, if you have built a vector store for a certain document, then it's not going to change. The vectors, like the vector embedding, is going to be the same. So then you check if the Chroma vector store already exists. If it exists, you just say, well, it exists. If not, you will read the content from the file. And then here you split the documents. So I have done character-based splitting, as you can see, and I have said the chunk size is 1000 characters. So every 1000 characters, I do a split, or I separate it. And then I, of course, ask to display the information because I want to see how it split all the chunks. And then for each of the chunks, I will create an embedding, and then I will add it to what we call a persistent directory, which is like the Chroma database that we spoke about, if you are building your own vector store. So let's see if I run this. So it's rag. So if I run it, it should say directory already exists. I'm running it on the bottom, by the way. So it says vector store already exists, and on here you can see the Chroma vector store. So if I delete this, let me delete it. And if I run this, yeah. So now it created kind of the document is a very simple document, by the way. It's just like a small section from one of the, what do you call, books called the Odyssey. And now if I look at my example here, I have asked it to print like one chunk. So you can see one chunk. So it has given my first 1000 characters, and actually it says it has 1003 chunks from the document, and it has given you a sample chunk. So sample set of information. And then it says creating embeddings, finish creating, and the vector store is created. So this is how you create a vector store. Now, if you take a step further, now you created the vector store, but you want to ask it some information. So the query, for instance, here. So you define the question and then you take this retriever. So retrieving the documents, and what I have done is similarity score that we spoke about in the slides. And this similarity score, the arguments you can give, this k equals 3 means if this similarity score finds 10 similar items, it's going to only give me the first 3. And the threshold can be from 0 to 1. And 0.9 or 1 means that it is 100% similar, and 0 means it's not similar at all. So you can play with these as well if you want to really do. I can send you one of these codes also. So here you can play a bit with the values, and then that is the retriever, and then it's going to retrieve the relevant documents, and then it's going to give you kind of the information. So I just have written Odyssey, which is a really bad query, by the way. I just wanted to test it. And then so I just ask one query there. This is not a full-blown conversation, or it is not integrated with LLMs. But if I want to integrate it with an LLM, then I have to do the same thing, embedding and creating the embeddings from the database and actually putting it in a Chroma DB. And then I'm going to create the OpenAI model. So here you need a API key actually, and that you can just go to OpenAI. You don't need to pay anything. I think you get a free trial, so you can just do it. But here I have done some prompt engineering. So this is what I wanted to show you. Everything else is almost similar, but here what I have said is, given the chat history and the latest user question, which might reference context in the chat history, formulate a standalone question which can be understood. Without the chat history, do not answer the question. Just reformulate it if needed, and otherwise return it as it is. So what this means is, when you are given a query, first this prompt is going to take it and turn it into a better question that the retriever can actually understand. So if I'm asking just Odyssey, or I'm asking who is the author of Odyssey, or who author Odyssey without the is and the, maybe it's going to reformulate it in a better way compared to previous questions that I have asked. And then I create a history-aware retriever, which means I'm going to use the persistent directory that I had again, and then I'm going to answer the question. So here you can see like multiple prompts that I have used. So why I use multiple prompts is you can also change the question that you asked into a better question. And also when you're answering, you should tell the LLM, this is how you answer. So you have to you can do it in both. And then it's going to get the information and basically retrieve the information from the retriever as we used before. And now in the retriever, you also have history-aware retriever, which means it's going to store the history of the questions that you asked in embeddings, and then you also have like the question that was asked. And then I'm going to simulate a continuous chat, which means the chat just doesn't stop from one simple question. So let's just run this code. This is Rabbit. So it should say now the directory already exists because we already created it. And now it says, yeah, type. So for instance, now we are talking about the book Odyssey. So if I ask who is the author in Odyssey, am I typing it correctly? Odyssey. Is it correct? The author of the Odyssey is traditionally attributed to the Greek poet Homer. So yeah, so for instance, I asked who is the author in Odyssey. I can actually increase the size. Okay, sorry. Yeah. So I asked who is the author in Odyssey, but the name of the actual book is The Odyssey. So here you can see prompt engineering of my question. So it's not answering about Odyssey, it's actually answering about the book, The Odyssey. And if I go to my text and if I want to double check who's the author, you can see the author is Homer. So it's good, it is correct. And you can ask multiple questions, but I will exit just because I just wanted to give you an example. But you can ask like when was it released, because you can see the release date, and then you also have like different chapters and information, so you can ask many questions. So this is just one document that is attached, but of course you can attach as many documents as you want. But yeah, this is a full-blown conversation you can have with RAG. Okay, let me. Okay, so yeah, I hope you learned something out of this. It was a bit fast, but and it was also, there was a lot of information, but I hope you learned about AI agents, agentic AI, and RAG. If there is somebody who learned absolutely nothing, I apologize. But I hope you got some information or you grasped some knowledge from this presentation. And thank you very much. And please feel free to ask me any questions. And if you want any more information, I'm more than welcome in giving. So thank you very much, everyone.
Now it's time to hear from you. We're opening the floor for your questions and comments. Please post them through Slido and we'll be bringing them to our speaker shortly. Thank you so much, Ms. Prashani, for sharing your insightful knowledge and experiences with us. Your work is truly inspiring, and the clarity with which you explain such a complex topic has made this session immensely valuable to all of us. As a token of our gratitude for taking the time to being with us and for sharing your valuable insights today, we would now like to present a token of appreciation to Ms. Prashani Jayasinghe. Your contribution has made a significant impact on everyone here, and we're incredibly grateful for it.
Thank you very much, everyone. I hope you learned something out of this, and I can also leave you my email address. Okay, so feel free to, actually I wrote it wrong, but I can write it here, but feel free to contact me anytime you like, and thank you so much again for inviting me.
Thank you. So before we conclude, let's capture this moment together. We kindly request everyone to turn on their cameras. The virtual background is already shared in the chat. All right, everyone, get ready. Let's count down. 3, 2, 1. Click. Again, please. 3, 2, 1. Click. Thank you all for being a part of this memory. So to formally conclude the session, I now invite Ms. Chatuni Karunaratne, the co-chairperson of HackElite 2.0, to deliver the vote of thanks on behalf of the IEEE WIE Student Branch Affinity Group of University of Moratuwa.
Good evening, everyone. As we come to the end of this wonderful session, it is my privilege to express heartfelt gratitude on behalf of HackElite 2.0. First of all, I would like to extend my sincere thanks to our esteemed speaker, Ms. Prashani Jayasinghe, for sharing the invaluable knowledge and insights. Your expertise has truly enriched our understanding and sparked new ideas. A big thank you to all the participants for your enthusiastic presence and active engagement. Your thoughtful questions and contributions helped make this session interactive and meaningful. I would also like to acknowledge the efforts of the organizing team behind the scenes. Your dedication and coordination ensured the smooth flow of the session from start to finish. Last but not least, a heartfelt thank you goes to the IEEE WIE Student Branch Affinity Group of University of Moratuwa for organizing HackElite 2.0 and for providing undergraduates this valuable platform to showcase their talents and enhance their skills through such an inspiring competition. Let's carry forward this learning and inspiration from today as we continue to grow and collaborate. Thank you once again and good night.
Thank you, Ms. Chatuni Karunaratne. Thank you to all participants for your engagement and enthusiasm. We hope today's session has sparked new thoughts, inspired fresh ideas, and opened your mind for the wonders of AI. Signing off, I'm Janati Kodikare. Until we meet again in our next HackElite 2.0 session, stay curious, stay inspired, and good night.